So this video is another in the series for MAT 1133 at UTSA. So this will be the first video on calculus. So we're starting chapter 11 in the textbook. So chapter 11 is on differential calculus. Section 1 is on limits. I'll preface this whole thing by saying that this video will be relatively short compared to the previous ones, which were fairly dense. So we're not going to spend a huge amount of time on limits. Conceptually, we need to know what they are, but we're not going to have to deal with them that much after this week. They're relevant, but after next week, they're relevant, but we're not going to spend a huge amount of time on them. In Cal 1, we would spend a good 2 to 3 weeks on limits, but in this course, we do less nuts and bolts under the hood stuff. We do more applications, so we don't need limits to be done as thoroughly. So the first thing I want to talk about is what I've got written here. What does it mean for x to be near to? What does it mean to have a number that's close to another number? And in an in-person class, I just ask, okay, what's a number close to 2? A common first answer is 3 or 1. Those are both pretty close, right? And I could ask, okay, is that really close to 2? Because there are numbers that are closer, right, or nearer. So like 2.5 and 1.5, those are both nearer to 2. And someone might say, well, we could get closer, right? What about 2.1 or 1.9? Those are closer, right? We all kind of get the concept of what that means. So something I want you to think about when we're talking about limits is if I have a number line, I'll put 2 in the middle because I'm focused on the number 2 right now. Then, a number like 1 is, close, and a number like 3 is close, but like 1.5 and 2.5, those are closer. And like 1.9 and 2.1, those are even closer, right? And if we could zoom in a whole lot, we can zoom in a little bit. We could say, oh, well, what about 2.01, right? And 1.95, and I'm running out of space here, but like 2. Oh, you know what? I made a mistake. That's 2.05. Sorry, halfway between 2 and 2.1 would be 2.05. Mistake there. So as I was about to say, I'm running out of space here, but we could say, what about 2.01 and 1.99? They're right there next to 2, right? So we're going to change gears a little bit. Would I say that 2 is near 2? Right? Would that be a reasonable thing to say? 2 is close to 2? Because close to kind of implies nearby, but not right at, right? Just in common language, how do we use this term, right? So if I say that x is near 2, I mean it kind of lives somewhere to the left of 2 on the number line or somewhere on the right of 2, but nearby, right? X is going to be somewhere. Oops, let me change that stylus size. X is somewhere over here or somewhere over here, right? But not equal to 2. When I say that x is near 2, it kind of implies not equal. So we're going to be a little bit to the left, a little bit to the right. So this kind of region, this is called a neighborhood of 2. And maybe that totally makes sense. That neighborhood would be the right word for that. If I were to say I went somewhere, but I'm meeting someone at my house later, and they call me up, they go, "Oh, are you home yet?" And let's say I'm say I'm walking, right? So I'm, obviously don't use your phone while you're driving, right? Unless you got the hands-free thing. So I'm walking back, and they call me up and ask, "Are you home yet?" And I go, "Oh yeah, I'm in the neighborhood." That means I'm down the street a little bit. I'm close, I'm just not home yet, but I'm nearby, right? If I were already at my house and they said, "Are you at home right now?" Would I say, "Am I in the neighborhood?" No, just say yes, right? So the neighborhood is the local area nearby, but it kind of means not specifically at that location, right? So think of it in those terms. Sometimes we'll want to include the number 2. We'll say, well, we want numbers that are close to 2, or also 2 itself is fine, right? And other times we want numbers near 2, but we do not want to use 2. So this idea of nearness is going to come up from time to time. This is basically the concept of limits hinges upon this being as clear as possible. What does it mean to be near a number? Okay. So let's talk about our first example. And let's not get there yet. So let's look at this function, and let's not worry about what this means just yet. We'll get to that in a moment. So f of x equals x squared minus 4 all over x minus 2. This is a function, right? The domain does not include 2, right? If I plug in 2, then if I try to do like f of 2, then I'm going to have 2 squared, right? Minus 4 over 2 minus 2. Well, that's 0 over 0, right? What does that mean? Right? And some of you might go, oh, well, that's 0, right? 0 over 0 is 0. That kind of makes sense. Some of you might say, well, isn't that 1? When you divide something by itself, you get 1. So it's not so clear. So before we proceed, I want to talk about what that means. Do I have horizontal space? Yeah, I have a little bit. Let me do this. Move that up here. So I have room over here. I'm going to change colors as well. So what does 0 over 0 mean? So I want to talk about just basic arithmetic a little bit. If I say like 8 over 4 equals 2, that's true. 8 divided by 4 is 2, but we could ask why. What do we mean when we say that, yeah, that's correct? Why is 8 over 4 equals 2? There's a couple ways to think about it, but one way is to think about the related equation 8 equals 4 times 2, right? The reason that 8 divided by 4 is 2 is because 4 times 2 is 8. That's basic kindergarten, first grade arithmetic, right? When you learn multiplication, you learn via repeated addition, right? And you learn about multiplication, and you are asked or required to memorize multiplication tables. And then once you've got that down pretty good, then you start learning division, and they'll say, okay, what is 8 divided by 4? And that means, what do you multiply with 4 to get 8? And because you've memorized it, you think about, oh, well, 2. 2 times 4 is 8, so the answer is 2. They go, yes, that's absolutely right. When you do division, you're thinking backwards through multiplication, right? So any division statement has an associated multiplication statement. So if I say something like 0 over 0, in fact, let's do this. Let's back up a little bit. Let's say I want to do, let's say 1 over 0, right? Because you can't divide by 0, so I want to examine this. If you say, oh, well, that equals, say, 0, well, look at the associated multiplication statement. If I take this 0 and transfer it to the other side as a multiplier, right, I'll get 1 equals 0 times 0. Well, that's false. That's not true, right? 0 times 0 is 0, not 1. And so no matter what I try to put over here, if I put something else, like, I don't know, 1 over 0 equals 1, perhaps? And we just do this transfer, put the 0 on the other side as a multiplier next to the other 1. So 1 equals 0 times 1. No, that's also wrong, right? That's just not true. So these statements are false because the associated multiplication statements are false, right? This one is true because this is true. These are both false because this is false, right? So we'll say you can't divide by 0 because there's no number you get that would make an appropriate multiplication statement. So let's look at 0 over 0. So if we say, oh, well, 0 over 0, that equals 0, might be the most obvious thing. Well, if we look at the associated multiplication statement, and in fact, what I'm going to do is I'm going to change colors here. I'm going to make this one purple. Well, let's make it red, so it stands out more, right? The offending 0 divisor. So I'm going to rewrite this as 0 equals 0 times 0. And we can ask, is this true? Right? Well, 0 times 0 is 0, so yeah, that's true. So does that mean this is true? Well, let's not jump to conclusions. What if I do 0 divided by 0, of course. Let's say that equals 1. Well, what's the associated multiplication statement? Well, that's going to be 0 equals red 0 times 1. Well, that is also true, but then this is sort of confusing. There's two different answers? 0 over 0 is two different things? How can that be? Because if these are both true, that means 0 and 1 are the same number. But of course they're not. So this doesn't really make a lot of sense. So you might feel like, well, it's starting to break down that this is an appropriate way to do things. But it's actually fine. It's just that when you get that the associated multiplication statement is just false all the time, well, then this is just undefined. 1 divided by 0 is undefined. okay? But when it starts to seem like, and I'm running out of space here, that's okay. When it starts to seem like you really could have anything there. 0 over 0 equals, say, x, right? X could be whatever. Let's just, let's say n for number, because I'm using x for something else already. N for number, well, the associated multiplication statement is 0 equals, oops, struggling with the interface here, 0 times n. Is that true? Well, 0 times n is 0. So, yeah? Question mark? This is what we call an indeterminate form. I'm running out of space here. Minute form. This format, 0 over 0, doesn't have a clear definition. Okay? So it's not merely undefined like 1 over 0. It's indeterminate. It could be something, maybe, but plugging 2 in here does not get us a result, a tangible or recognizable result. We don't get anything. But I could say, and that's why we say that 2 is not in the domain. You can't just plug in 2. You get an indeterminate form. It doesn't work, right? So really, f of 2 does not equal that. F of 2 isn't anything. But I could ask a related question. What should f of 2 be? And I'm putting should in quotes because I'm sort of working by analogy here when I say should. The answer is it isn't anything. F of 2 is undefined. 2 is not in the domain. When I say should, what I mean is, well, if we were going to change the function and assign a value, could we pick something for f of 2 to be equal to that would be consistent with what the function otherwise does? So based on the behavior of the function in the neighborhood, so what's the function? What should f2 be? Comma, based on the nearby behavior or the behavior nearby. So there's that word, near, right? When you try x coordinates near to, what does the function do? And there's 3 basic ways to approach this. There's numerical, which we're going to do in a moment. There's graphical, which is farther down the page. And then there's algebraic, which is farther down the page. So let's do this numerically first. If I pick some numbers that are close to 2, and I'll probably have some room here to do a little bit of arithmetic. If I plug in, like, say, 1 for x, and we'll start from the left. Let's start with lesser numbers, and we'll go like 1, 1.5, 1.9, and so forth. If I plug 1 into my, not plug, a small dog. If I plug 1 into my function, what do I get? And this might be really simple, especially with a whole number. But I would encourage you to double check that these are correct. I'm going to tell you what I think they are, but you should check these for yourself. Do it by hand or use a calculator or whatever. So if I plug in 1, I'm going to get 3. I'll do this first one. I'll show this first one directly. So 1 squared minus 4 over 1 minus 2, right? So 1 minus 4 is negative 3. 1 minus 1 is negative 1, and I get 3. So 3 is the outcome, right? Okay. What if I put in 1.5? Well, it turns out, and you should check this for yourself, but, I just, I've done this problem enough that I remember the numbers, and just for expedience, you get 3.5, okay? If you plug in 1.9, what do you get? In here, you probably would want a calculator at this point. This would be kind of hard to do by hand, or tedious. Not difficult, but tedious. Well, you're going to get 3.9. Okay, what if you put in 1.99? You're getting really close to 2, right? Like up here on this number line. We're getting really close to 2 right here, right? There's 1.99. It's hard to see, but there it is. We're getting really close to 2. Well, if you work that out, you will get 3.99. Okay, so the top row, this is getting close to 2. That's what it's approaching. Another term for this is approaching. We're picking numbers near 2. And as we go along, we're picking numbers nearer to 2. We're approaching 2 in the x-coordinate. Well, what happens in the y-coordinate? Where is it going? and pause the video and think about it. Maybe it's obvious, maybe not, but take a minute to think about it if you need to. What are we getting closer to? So now that you're back, we're getting closer to 4. So if we are checking numbers to the left of 2 and getting closer and closer, the results of the function appear to be 4, or getting closer to 4. Okay. So that does not quite answer the question, because it's possible that if we check from the other side, start with numbers bigger than 2 and then get closer to 2, we might not get 4. So we have to check that. So let's try the other side. I got another table down here. So let's try starting at 3. Right? Okay, so what's f of 3? F of 3, that's going to be 3 squared minus 4 over 3 minus 2. So 9 minus 4 is 5 over 1, so 5. Okay, so we get 5. What if we put in 2.5? That's between 3 and 2, right? Being closer to 2. Well, I'll work this one out. This one isn't too bad, I guess. So 2.5 squared minus 4 over 0.5 minus 2. So you might recall, you might know this one. If you were required in middle school or high school to memorize some of these, maybe you know this one. And if not, use a calculator, that's fine. So 6.25 is 2.5 squared and minus 4. And then on bottom we have 0.5. So I've got 2.25 over 0.5. And here's a little trick that you might be aware of, perhaps not. Of course, you could use a calculator. I'm going to double the top and the bottom, and I get 4.5 over 1, which is 4.5. 4.5. Oh, you got a little bit closer to 4, right? If you put in 2.1 and you work it out, you'll get 4.1. And again, you should confirm these. Make sure that I'm not making this up, right? You should confirm this for yourself. What if I put in 2.01? Well, you should get 4.01. 0.1. So in the top row, as my x coordinates get closer and closer to 2, where does the y coordinate go? And maybe it's obvious, maybe not. Take a minute to think about it. So the y value gets closer and closer to 4. Aha, these two agree. I'm getting closer to closer in 4 when I check from the left, and I'm getting closer and closer to 4 when I check from the right. This is the concept of a limit. When you are examining the behavior of the function it inputs to the left of the number you're asking about and to the right of the number you're asking about, if there's agreement, oh, that means I get a limit. So here's what we'll say. In this case, to summarize this table, we'll say that the limit LIM, this is the notation, as x goes to 2 with a little minus, okay, from the left, that this is, and I call it f of x, it's of course this guy, okay, that this is 4, okay, and then this, to summarize it, this means the limit as x goes to 2 from the right of f of x is 4, okay. As you may have noticed from looking at the syllabus, the way this book structures things is it puts what are called one-sided limits. When I say from the left, this little minus sign means that we were doing like 1, 1.5, 1.9. We're getting closer and closer to 2 from the left side of the number line. And then this little superscript plus 2 from the right. This means we're going like 3, 2.5, 2.1, 2.0. We're coming from the right-hand side of on the number line, right? That's coming from the left versus from the right, okay? The way this book structures things is it actually handles one-sided limits in section 2. So I'm only going to mention them once here. We'll get a little bit more exposure to those later. But it's just in our first example of a numerical limit, I prefer to explain it this way. So when those two things agree, we have an agreement among those two values. We'll say, oh, that means that the limit as x goes to 2, not x equals 2, right? Because remember, f of 2 is undefined. We get an indeterminate form, 0 over 0. You can't do f of 2. It doesn't work. But the limit, which means what's the behavior nearby? Do we get a consistent pattern of the behavior nearby? Yes. In this case, we get 4. 4 is the limit of the function as x goes to 2. Okay, so this concept is it's basically the foundational bedrock of calculus. Without treating the limit in some way and talking about what a limit and understanding what a limit is, you can't do standard calculus. There's something called non-standard calculus, but that's extremely complicated. We're not doing that, of course, in this course. Said course too many times. Anyway, so that's our first example of doing a limit numerically. And I say, what should the function be? Because if we were to say, well, you know what, let's look at the graph, I think you'll see what I mean. So next we're doing this graphically. Oh, algebraic. Let's do that later. So if you graph this function, especially if you have a computer do it for you and just look at it, you might be surprised, maybe, to see that the graph is just a straight line. And you might say, well, no, but we talked about linear functions, and linear functions are mx plus b. Is this mx plus b? Well, no, it's not, right? It's a quadratic divided by a linear. So how could the graph be linear? Well, let me make a rough sketch of what it would look like. Let's say that's good enough like that, right? Okay, so this x-coordinate is 2, okay? Because if you plug in 0, you get, I'm sorry, this y-coordinate rather, sorry. If you plug 0 into the function, you get 2 as a result. So if I go look at here where x is 2, and here where y is 4, then in the graph, if you have a computer do this, it might look just like this. It doesn't necessarily do what I'm about to do. What I need to have is a little teeny tiny gap right here. In fact, let me do it this way. Let me make a straight line. So I'm looking directly above 2. I need to have a little gap right there in the graph, okay? And then I can say, oh, well, actually what happens is there is a little gap there. There's a hole in the graph because f of 2 is undefined, right? We said that earlier. F of 2 is undefined, so there actually isn't a value there. There's no point on the graph at x equals 2. There's a gap. Otherwise, though, the graph is a straight line. And so if you think about it, what's the behavior nearby? Well, as we were checking, let me change colors here. As we were checking values, like at say 1, x equals 1, x equals 1.5, x equals 1.9, x equals 3, x equals 2.5, x equals 2.1, we're zooming in on that location and looking at what's the pattern in the y coordinates. So when we put in 1, right, which would be this point here, we got 3. When we put in 1.5, which is this point here, we got 3.5. Right? When we put in 1.9, which is here, right, we got 3.9. Right, and I'm running out of space to do like 3.99. And then on the right, this maybe I don't need to go through all these steps. It's fairly clear. But if I go to 3, that's this point right here, and we got 5. And if I go to 2.5, that's this point like right here, and I got 4.5. Right? And if I go to 2.1, it's this point here, and I got 4.1. When I zoom in on 2 in the x-axis, I'm zooming in on the graph, and therefore I'm also zooming in on the y-axis. What's the behavior of the y-coordinates? And when I get close to 2 in the x-coordinate, I end up getting close to 4 in the y-coordinate. That's the concept of a limit. And you can do this, sorry, let me erase that. Yeah. So we can do this numerically on a table, right? Like these tables here. I can look at a graph, and basically I've had a computer do the calculation for me. It's representing the numbers in the table, right? It's representing them visually here, and I just look at it. I can tell what the limit is just by looking at the graph, right? So if I were to say, oh, what's what's the limit of this function as x goes to 3? Well, you just look at it. Well, when x is 3, it's right here. Just look at it. Oh, well, there's no gap, so it's just 5 is the answer, right? If you had a different graph, well, you just look at it. What is the behavior? If you have some different function and you had like this, and your graph is shaped like this, right? It's some weird function, and you're looking from the left as, say, x goes, I don't know, is that 7 or something? Say 7. So as you're following along, what's the y coordinate? What's the y coordinate? What's the y coordinate, right? Well, you end up at like 3, I guess. Maybe the limit from the left is 3 for that one, right? And then as you look at coming from the right, what's the y coordinate? What's the y coordinate? As you move along the graph, what's the y coordinate all the time? Maybe you end up with 4, and there's a disconnect. The two sides don't meet at a central location. The two numbers are different. So just like these two numbers are the same, we got 4 in both cases, doing this numerically. In the graph, when you come from the left and come from the right on the graph, you end up at the same location. Y equals 4 is the height level. So hopefully that made sense, just visually, that's maybe even more straightforward than doing these numerically. I think once you look at both of these things, you'll see, yeah, this is really the same thing. Doing this numerically was kind of tedious. Obviously, in order to graph it, you have to already know that. So I was skipping a lot. I already know what the graph looks like. So now let's get into the algebraic part. How do I know this is what the graph looks like? Where did I pull this from? Did I have a computer do it? How did I get this? And I just realized I probably should say algebraically, since I'm using adverb forms here. I should probably be consistent in my language. Algebraically, not just algebraic. So how do I deal with this algebraically? How do I identify what the function's, in quotes, supposed to be? Well, what I'm going to do with this one is something that you might expect. In an in-person class, I would probably ask, okay, guys, what should we do with this to simplify it? And someone might go, oh, well, let's factor the numerator. So the numerator is a difference of squares. So I can factor the numerator. Sorry, struggling with the interface a little bit. And I get some cancellation, right? I have x minus 2 on top and x minus 2 on bottom. So I get, oh, well, this is just x plus 2. That's why it's a straight line when you graph it. But I want to talk about this right here a little bit, this equal sign. Or rather, this, let's say it's this step. When I do this cancellation, I'm changing what the function is. Because clearly, because of the cancellation, these two things are equivalent. Like if I plug in 1 over here, I get 3. If I plug in 1 over here, I get 3. Right? If I plug in 3 over here, I get 5. If I plug in 3 over here, I get 5. They're equivalent, right? However, if I plug in 2 over here, I get nothing, undefined. If I plug in 2 over here, I get 4. So they're not the same. There's a difference, right? When I make this cancellation, I'm changing the domain of the function, okay? So as functions, although we say that these two things are equal, as functions, if I say g of x equals x plus 2, and if I ignore all this for a second and just focus on these two guys, these are not the same function. Their domains are different, right? And without examining and simplifying the top function f of x, you might think, oh, those look totally different. Of course, if you keep this in mind, you go, oh, well, actually, they're effectively the same. The result is the same when you plug numbers in, right? But if you just look at these, they look different. And the main difference that might be most obvious is, well, one, this is clearly linear. This one's a rational function. But also this one, because it's a rational function, the domain does not include 2, right? For this one, the domain seems to include 2, right? So that's something to keep in mind. When you do cancellation in a rational function, you are changing the domain, or in other words, you are hiding the domain. Like I could say, oh, well, no, this is still x plus 2. It's just that the domain of f does not include 2. Therefore, this formula does not accept 2, because in principle, 2 was never allowed, so it still isn't. Okay? That's going to become important later when we do examples involving cancellation and substitution. We'll go over that when we get to it. So, how do I find the limit this way? I think, yeah, I got some examples there. So how do I deal with the limit this way? Basically, I can do this. I can say, okay, I have the limit as x goes to 2 of x squared minus 4 over x minus 2. I can do the factorization, or if I want, since I've already written it out up here, I don't have to write it again. Oops, don't need that. Well, I can say that this limit as x goes to 2 of x squared minus 4 all over x minus 2, this is equal to the limit as x goes to 2 of x plus 2. When you make this cancellation, that doesn't affect the limit value, because remember, the limit is entirely about what is the behavior nearby, what is the behavior in the neighborhood. So these two functions are only different for the input 2. They are otherwise the same, right? Like the graph of g of x is this graph here without the hole, without that gap, right? It's just a straight line with no gap in it. So these two functions are the same for all the inputs except for 2. But the key thing is the limit specifically says don't use 2. 2 is not an input for the limit, right? We're inputting things nearby. But there's not an exception to that, but there's a convenience to that. These two things are identical because we're never using 2. However, when you have a limit of a function where you could just plug it in and get a result, it's always going to happen that that is a thing you can do. You get the right result that way. So now I can say, well, let's just plug 2 in and get 4. So these two equal signs mean very different things. They're working for different reasons. This equal sign says, well, because we're doing a limit, we're not using 2, I can switch from one format to the other. I can switch from the non-simplified rational function to the simplified linear function, and that's okay because we're not using 2. The second equal sign, says, okay, forget all about what happened here. It's not relevant anymore. This equal sign says, well, we could just plug in 2, which might seem like, wait a minute, aren't we contradicting ourselves? Well, they're two separate steps, so it's okay. In the first step, we are going to say, well, we're not using 2, so these functions really are the same thing. In the second step, well, we could just plug in 2, which might seem contradictory, but as long as those are separate steps, that's okay. So that's our first example of an limit done algebraically. Let's go do some more. How about this one? Let's say I want the limit as x goes to 2 of 3 over x minus 2. There's no cancellation. And if I plug in 2, right, is this equal to 3 over 2 minus 2? No, that'd be 3 over 0, right? That's not an indeterminate form. That's merely undefined. You can't divide by 0, okay? But that's not necessarily a conclusion about the limit. The limit could still be something. So here's what we have to do. We can do this numerically. We can do this graphically. There's a way to do it, not algebraically, but what's called analytically, but we don't need to do that. That's going to be maybe overly complicated. Let's do this numerically and see what we get. So how much space do I have? Oh, quite a bit. Okay, let's do this numerically. Let's make a table. And then maybe we'll look at the graph as well. So that is larger than it needs to be. Okay, so let's say I have x here, I have y here. Let's plug in 1. Let's go to 2 from the left first. If I plug in 1, if I plug in 1, what do I get? Well, we get -3 if you plug that in, right? If I plug in 1.5, what do we get? Well, 3 over 1.5 minus 2. That's going to be a, what, -6? Okay. How about 1.9? 3 over 1.9 minus 2. I believe that's -30. I'm pretty sure that's right, but let me get a calculator and check that out to be sure. So 3 divided by 1.9 minus 2. Yeah, -30. Okay, what about 1.99? That's going to be a -300. Okay, so as the input gets closer and closer to 2 from the left, from below, and this might be obvious, maybe not, so think about it, pause the video and think about it if you need to. Where is the y coordinate going? And you might recall from algebra class that this function has an asymptote. It has a vertical asymptote at x equals 2. We'll look at the graph in a minute. So what's happening is the y-coordinate is going to negative infinity. Okay, not a number, but that's a place. Basically, it's all the way down vertically on a graph. It's just down. Okay, so let's clear this out. Let's do the other side. What about as x goes to 2 from the right? Let's start at 3. So if I plug in 3, what do I get? Well, I get 3. If I plug in 2.5, right? So 3 over 2.5 minus 2, I get 6. Okay, if I put in 2.1, so 3 over 2.1 minus 2, I get 30. You might be noticing a pattern here. If I put in 2.01, okay, so if I 3 over 0.01 minus 2, I get 300. Okay, so as I go to 2 from the right, the y-coordinate goes to positive infinity. So these two guys, these are different. I do not get the same result. Okay, so we'll say that this limit is undefined because we got different results. On the earlier example, we got 4 from the left and 4 from the right, so 4 is our answer. Here we got negative infinity on the left, positive infinity on the right. They're different, so we get nothing. If we had gotten negative infinity on both, well, then the answer would be negative infinity. That would be the limit. The limit doesn't have to be a number. It can be infinity or negative infinity, but you have to check both sides. And if there's agreement, then you get an answer. Here, we get nothing, undefined. If you look at the graph, I guess I have room over here to sketch this. That little bit. The vertical asymptote is at x equals 2. So indicate the asymptote like that. So the graph looks a little bit like this. Obviously, I'm not going for perfection, just kind of close. Okay. So when you plug in, say, we did from the left first. Yeah. When you plug in 1, here's 1. You look at this point, we're at like -3, right? You plug in 1.5, we're down here at -6. You plug in 1.9, we're down here at -30, right? Now, obviously, the scale is not right. I'm doing this by hand, but hopefully you kind of get the idea that as you, in the graph, as you move closer and closer to the asymptote and you follow the graph down, you go down to negative infinity, okay? On the right, if we go to 3 first, 3. Say 3 is like right here. Well, you got a point right here. We're at height 6, right? If you go to 2.5, well, we're up here at height 30, I think. Is that right? No, 3. Sorry. If we plug in x equals 3, then on the graph, we're here at 3. We plug in 2.5 on the graph, we're up here at 6. Plug in 2.1, we're way up here at 30, right? The scale is off, but you get the idea. I'm doing this by hand, so it's not going to be perfect. So as we follow the x-coordinate to 2, and we follow the graph up to positive infinity, okay? So when I go to make this graph, because I've done this first, I know that when you go to the asymptote from the left, because the limit's negative infinity, because I did it numerically, so I know that going into the graph, I know this goes down, okay? And because I've done this ahead of time numerically, I know that when you follow the asymptote, I'm sorry, not follow, but you get closer to the asymptote from the right, the graph goes up because I got positive infinity, okay? So when you have something that appears to be, where is it? 0 over 0, when you plug your number in, that means you're probably gonna have to do some algebra. You could do it numerically or algebraically. There's some work you gotta do to find out what's the result, okay? And often an algebraic approach like this one will often work, okay? If you have something that gives you 3 over 0 or 5 over 0, then you're not gonna get a number. You'll either get infinity, like if the graph were different. Say the graph was not like this, right? If the graph went up on both sides, then there'd be agreement. The limit from the left, following this would be positive infinity, and the limit on the right would be positive infinity. So you would get the same result. You go, oh, well, the limit's infinity. The graph goes up on both sides of that asymptote. Or, of course, if the graph wasn't like this, and the graph went down on both sides, then the limit would be negative infinity. Maybe we'll have some like that. I've forgotten what's next on the list here. Anyway, so that's dealing with a limit where you are not going to get a number, but you might still get a conclusion, infinity or negative infinity. And the key thing is checking the left, checking the right. Is there agreement? Do I get the same result? So next, let's look at this one. This one, let's go ahead and do this numerically as well. And then we'll look at the graph as well. Okay, so that there, and get rid of that. Okay, so x, y. So x is going to 0. So if we want to start from the left, we're going to have to start with negative values. So -1, if we plug it in, what do we get? Well, the absolute value of -1 over -1, well, that's 1 over -1, which is -1, right? So -1. Awesome. How about -0.5? Okay, we're getting closer to 0. We're getting closer to 0, right? Okay, well, the absolute value of -0.5 over 0.5, well, that's going to be, almost made a mistake, -0.5, because that's what we're plugging in, -0.5. Well, that's going to be 0.5 over -0.5. If you work that out, you'll find that you get -1 as a result. Okay, -1. How about -0.1? Well, if you work this out, absolute value of -0.1 over -0.1, well, that's going to be 0.1 over -0.1. Well, if you divide that out, you get -1. So we get -1. So the result's always -1. So as we get closer to 0 from the left, we get -1 in the y coordinate. Okay, so I'm going to get rid of all this, and then we'll do the other side, and then we'll look at the graph after that. Okay, so let's do the other side. So I want to come at 0 from the right. So we'll start with 1. Okay, if I plug in 1, what do I get? And I'll skip writing it out this time, but you'll have 1 over 1, right? The absolute value of 1 is 1. So I'll have 1 on top and 1 on bottom, so I get 1. If I plug in 0.5, well, I'll have 0.5 on top because it's already positive. The absolute value bars don't do anything. Divide by 0.5. Okay, well, I get 1. Oh, you know what? We forgot to do something, but that's okay. We'll get to it in a moment. What about 0.1? Well, if you work that out, you get 1. So what about 0.01? Well, you get 1. So as we approach 0 from the right, the y-coordinate is just consistently 1. And notice how these two numbers are different, right? So the limit does not exist. And I'm going to abbreviate DNE just for convenience. So what I forgot to do, and some of you might be shouting at your screen, hey, he forgot to do such and such, right? I forgot to just plug in and see what happens. Oh, this is indeterminate. Right? So that means that plugging in doesn't work. It doesn't get me a result. Okay? That doesn't mean that I'm done, and I ought to do this first, because sometimes plugging in works. You get a number and you're done. So then I go to do this. I go, oh, well, the limit does not exist because I got two different conclusions here. I got -1 looking from the left and +1 looking from the right. So what does the graph look like? Well, if you graph this, you get something like the following. Okay, so let's say here's a 1, -1, 1, 2, 3, -1, -2, -3. Okay, so what happens is you're gonna get an open circle here and here, and you're gonna get straight horizontal lines extending out from there. So as you look at the graph from the left, as you approach 0, right, you're plugging in, say, -2, you're plugging in -1, you're plugging in -0.5, you're plugging in -0.1. The y-coordinate is consistently -1. So the limit from the left is -1, as we found. From the right, you plug in 2, you plug in 1, you plug in 0.5, plug in 0.1. The output is consistently, the y-coordinate is consistently +1. So the limit from the right is +1. And since those two numbers are different, they disagree, there's a disconnect. This is called a jump discontinuity. We will discuss continuity just a little bit when it comes up. In a Cal 1 class, we'd spend like a couple of days on it. We'd spend time on it, but we're not going to do that here. We don't need it that much. But conceptually, hopefully that makes sense. If you're a person walking along, it looks like he's running to the left, but actually just very badly. He's actually moved to the right. Once you get over to here, right, you're going to have to jump up to get to continue running on the function, right? So it's called a jump discontinuity for that reason. Okay, so what's next? Yeah, okay, so these are going to be some easier examples. Basically, this is something I talked about earlier. When you have a function, well, a limit of a function where plugging in seems to get you a result, like there's no reason that I can't just plug in 2. In other words, when it happens that the number where x is going is in the domain of the function, then you can just plug it in and that will work. Okay. There are some exceptions, but generally you just plug it in. So this is 2 plus 2, which is 4. There are some technical details that we don't really need, so we're not going to worry about them. How about this example? Is 7 in the domain of this quadratic function? Well, yeah, the domain of a quadratic is all real numbers. So just plug it in. So if the number where x is going is in the domain, you don't need to do the table or the graph or any algebra. Just plug it in, get a number. It's when plugging in 7, in this case, plugging in the 7 or the 2 or whatever it is, when that creates a domain problem, like division by 0 or the square root of a negative or whatever. That's when you have to be careful. So this will be what, 49 minus 14 plus 4, so 39. There you go. That's the limit. And if I were to do this numerically with a table, I would end up getting 39. Okay. But this one. So this one, and it looks a lot like the one we started with, right? We have x squared minus 9 over x minus 3. You might think, oh, we're going to have to factor. No, don't do that yet. Because it's 3 that's not in the domain, and that's not what we're asking about. We're not asking x goes to 3, right? If we were asking x goes to 3, then yeah, we would have to, factor and cancel and all that. But we're not. So I'm just going to plug it in. 2 squared minus 9 over 2 minus 3. So I get, what is that, -5 over -1? I get 5. And we're done. I don't have to do anything else. No cancellation needed. So whenever you have a linear function, a quadratic function, a rational function, as long as there's no domain problems, you just plug it in. Okay. So last thing here, let's talk about continuity a little bit, because the functions that are continuous are the ones for which that works. whenever plugging in just works, that we call the function continuous under those conditions. So let's say, given a function f and some real numbers, okay, C and L. C is going to be where x is going. L is the value of the limit, which is what this says right here. If the limit as x goes to c of f of x is L, then there are three possibilities, three possible outcomes, given that the limit is a number that you get, okay? Well, the first possibility is that f of c is undefined. This is what would happen with what's called a removable discontinuity, where that was the first example. Our first example, x squared minus 4 over x minus 2, that one, that's what happened here. The function's not defined at all. Plugging it in doesn't work, okay? So that was example one. Another possibility is that the function is defined, f of c is defined, and the limit and the function value agree. That's what happened with these three, okay, where plugging in works. Under these conditions, or under the situation rather, the function is said to be continuous, okay? So let's make a note. These are the continuous functions when that happens. And we'll talk a little bit about those in a second. The third possibility is that the function is defined, but the limit and function value are different. That's going to happen sometimes. Basically, this is another type of what's called a removable discontinuity. Some functions will do this, where the function is defined, but the limit is different. That's very rare. That's usually not going to happen. And for the kinds of functions we'll deal with in this class, that's going to be extremely rare. 9 times out of 10 in this class, we're going to deal with functions that are continuous anyway. This is one of the reasons why we don't spend a whole lot of time on limits in this course, because it's relatively easy to deal with most of the time, 9 times out of 10. So what are the continuous functions? What is the list for which item 2 will happen? Well, this will be all linear functions, right? All quadratic functions, right? All polynomials in general. All radical functions, with an exception when you have which we'll deal with later, but basically, but you have to be careful about domain for those. Okay. Exponential functions, logarithmic functions, and if you took pre-cal at some point, all the trigonometric functions, which in this course we don't deal with trig functions, but those are continuous on their domains. Okay, so basically that's section 1. This video ended up being a little bit shorter than I was expecting, but that's it for section 1. In the next section, we'll get a little bit more detail on some special types of limits, a little bit more detail on limits for one side or the other, and then also limits where x goes to infinity or negative infinity.